Hello everyone, welcome to my second video going through the 2025 VCE Algorithmics exam. In this video I'm going to go through all of the written answers. Now you might be using this just as an autopsy for the exam you've just done. If you're using it as revision, I encourage you to pause as you go along and make sure you try the questions. I'm going to be showing you some good answers and some bad answers, trying to show you the kinds of mistakes that people make as they go along. Note that I'm not affiliated with VCAR, these are just my suggested answers, and at the time I'm recording the video, the report hasn't even been published. So feel free to leave any comments or disagreements in the comments. Here we go. Make sure you pause, have a read. I'll remind you every single time. What do we think of this answer? Now, with signatures, we actually don't care what the operation does. We just care about the inputs and the outputs. So this might get some marks because we've acknowledged we are looking for two sets as inputs, but all we really need to say is that is equal takes two sets as inputs and returns a boolean, true or false, as an output. We don't need to say anything else. Number two. So we're going to start with this 2, 13, 8, 5. First we pop, then we pop, then we push 6 on top, so we now have 6, 8, 5. We pop the 6, we push a 2 onto the top, and we push a 7 onto the top, and then we pop the 7, and we are left with 2, 8, 5. These questions are always done worse than they should be because I think people rush into them and they write down the first thing they think of without having read the scenario over and over. The key thing to remember as well, whenever we are given a number in algorithmics, we need to pay attention to it. So it's easy to ignore the fact that these things have 5 to 20 steps. So when we look at some potential advantages, we don't care how fast this is because this could be accessed in exponential time even. Well, probably not exponential time, but it doesn't need to be fast to work. So I'd say that's the first mistake people can make here. The advantages I've put here, I'd say they make two mistakes. So stores the data in order, that's fine, that makes sense. Allows the first and last item to be accessed. Well, this alludes to what I was saying. It allows the first and last item to be accessed quickly, if that's what we're interested in, if it's a doubly linked list. Now you see in my other videos talk about the difference between single linked lists and double linked lists. Algorithmics doesn't really make the distinction. So I probably wouldn't allow this one, or if you got it, it would, it would be lucky. Easy for the user to read. Well, this is not how the things are being stored for the user to read. This is about how things are being stored inside the computer. So I wouldn't allow this one either. Let's find some disadvantages. Well, I've made it clear, it takes up a long time. That is not going to get anywhere. However, I think requires duplication of information is good because we can imagine that a lot of these things are going to be repeated. Whether you have to make a certificate of destruction, that sounds like something you'd be doing a lot. So I think requires duplication of information is a good one. Alternatives, well, you could have said a dictionary or an array. They would both make the same mistake. Again, this idea that speed matters in this case. They are appropriate ADTs, but they don't really have an advantage. The one, and I found this hard to come up with until I really gave it a lot of thought, the one that works well is a directed graph or a decision graph, which allows us to show the interactions between the steps. So we might first ask, well, is the hard drive, has it been reused within the company? That might be one thing, which then leads to a whole bunch of different decisions to make. So I think that would be the best alternative, and that would be the advantage that we could show the interactions between the steps and we wouldn't have to have duplicate data. Right, well, we'll just go through this one step by step. For each node, add it to the graph. So 1, 2, 3, 4, 5, 6. Now we're going to do a little trace table. U and V. U is 1, V is 3. While U is less than 5, which it is, while V is less than 6, which it is, we're going to add edge U, V to G. Now I'm going to do directed edges. I don't think we would need to. I think you'd get away with undirected edges. It doesn't really say enough. But let's put that in so you can see if it was right if you did a directed edge. Then V equals V plus 2, so v is now 5, and we're still within that inside while loop, so we add 1, 5. Okay, that was all inside this inside while loop. Then we would make v equal v plus 2, which is 7. Now looking at this inner while loop, we wouldn't do that again. Now we'll say while u is less than or equal to 5, which it is, u equals u plus 2, which is 3, and v equals u plus 1, which is 4. We go back to the top of that while loop. While v is less than or equal to 6, which it is, we add 3, 4. Let's go around the back that way. V equals v plus 2, so it's 6. Add edge uv again, so that's 3, 6. V equals v plus 2, which is 8, but now that inner v loop stops working. U is less than or equal to 5, so u equals u plus 2, so u now equals 5. V equals u plus 1, which is 6. Now we add 5, 6. And what do we do? We do v equals v plus 2, which makes it 8, so that breaks the inner while loop. U is less than or equal to 5, so that's fine. So u equals u... Well, actually, we're not asking the question yet, are we? We're just continuing on. So u equals u plus 2, which is 7. V equals u plus 1, which is 8. We're back to the top of that while loop, and that condition is now not satisfied. So we have our final graph. Questions like this, draw the trace table, and if you get a chance, go back and check it. Maybe just do it again, because so far all the questions have been, perhaps without question 3, the questions have been fairly straightforward. Like, we shouldn't be making any mistakes. So in terms of pacing, we need to be going fast enough that we're getting through them, but not so fast that we make dodgy mistakes. Yay, a lovely bit of Bellman-Ford action. Make sure you pause, have a go. I've got some wrong answers here, which are subtly wrong. I'm not going to go through exactly how Bellman-Ford works. I'm sure I've made a video or will make a video explaining that. So we do have to say infinity. In practice, if you knew you're dealing with single-digit numbers, then adding a ridiculously large number will be fine. But this is a general algorithm, so we need to account for everything. We'll say infinity. This one here, this should be greater than. We're saying if it's easier to get to v by going first to u and then from u to v, then we will set the new distance of v to that distance of u to v. And C is almost right. Negative edges aren't a problem. It's negative cycles which catch us out. So what we're doing from lines 10 to 12 is just running the process again. And if anything has changed, then we'll get that error that there are negative cycles. So if we find that we're able to relax even one distance, then we'll return that negative cycles error. Okay, what do we think? Now this answer is correct, but it's definitely not everything. I think we're trying to show off. Are there any numbers we're told? Yeah, kind of. I mean, we can see it's better. It's kind of implied in the red answer is that, well, it's better, but it's still very slow. I would want to see something like it's exponential. Both running times are exponential. So we know that Sophie's is slightly better, but still no good for finding very large numbers because both of them explode. Now, people often confuse the phrases exponential and combinatorial explosion. So make sure we know which one is which. If we have n factorial, we know that's a combinatoric explosion, whereas this is an exponential explosion. Part B, it's almost unrelated, but it was a way of sort of linking them together. Now I'm going to give you a few bits of pseudocode. I mean, obviously pause, try running it yourself. Let's have a look at a few of these answers and see what's wrong with them. Now, have a look. What do you think? Yeah, problems here. We can see we haven't defined the first two terms because you can't define a recursive sequence. Even though this is an iterative algorithm, it's still a recursive sequence. It refers to previous terms unless we have something to start from. Also, this one does not return any value, so that's no good. It is dynamic programming, at least. Like, it's got this idea of cycling over an array and building up solutions incrementally, so that's good. What about the next one? Well, we fixed that problem not having the values, and we seem to be working backwards. I mean, and we can actually work through this. So we can say, I would just do an example. Let's say n equals 5. We'd say, I've got my array here, dp, length of 5, so 0, 1, 2, 3, 4. The value of 0 equals 1, 1 equals 1. For I equals 0 to n minus 1, well, that's a problem, isn't it? Because we started at 0, and we're now referring like 2 steps back. So we really need to start from 2 here. So 2, dp of 2 is dp of 1 plus dp of 0. So it's 2, and then 2 plus 1 is 3, 3 plus 2 is 5, and we return. No, it's not dpn, is it? It's going to be dpn minus 1. This is one of those cases where I would rather use one indexing in my array than potentially make a mistake with returning n when, it seems intuitive to return n, doesn't it? Or dp of n. One more of these to look at. Now you might be looking at that thinking, well, is that really dynamic programming? Maybe. I would not do this as a first option, but let's see if it works for us. So, because we are sort of building up solutions as we go, but we're just not doing it in such a way that we could refer back from, let's say we're on term number 10, we don't then know what the first term was. But it's not necessarily required for dynamic programming. So, choose your own adventure, roll the dice, all that. So let's say n equals 5. A equals 1, B equals 1, I equals 1. Now C equals A plus B, which is 2. A equals B, which is 1. B equals C, which is 2. I equals I plus 1, which is 2. Is I less than or equal to n? Yes, it is. So we go through. C equals A plus B, so that's 3. A equals B, which is 2. B equals C, which is 3. I equals 3. And I is still less. Let's just skip through. Okay, we get to this point and we've finished that last loop where I was less than or equal to 5. Now, in this case, we've returned C, which was 13. So I think we can see two problems with this. Like we found too many numbers, so we should really have started with I being 3. That would be one way of fixing this. What we could have done is, first off, make this less than n. So that would mean we would have stopped here. And then we would not return C, but we would have returned A. And that would have worked. So that's not perfect in that we are writing a slightly wrong algorithm and then fudging it. But hey, that's better than getting an algorithm wrong. With these coding questions, if you'd written down the answer on the right just as it is, you probably would have got at least half the marks. So you got to use your time carefully and decide, well, maybe I will just write down something that's okay and then go back and check it later on. Okay. A linear classifier. Well, hopefully, I mean, just imagine that is a straight line. I'll have to label it straight line. Really should have animated that in the PowerPoint. I don't want to change it now. That should have been a gift for everyone. As long as you didn't do this. Ugh, no. Right, what do we think about this as a solution? Well, maybe it's a little bit close to a circular definition. Like if we'd said, for example, because they can't be separated by a linear classifier, that would have been 100% circular. Linearly separable, you might get away with, let's just say the obvious. They are not separable by a straight line. By a straight line. It's only one mark, and I imagine people might get tempted into talking about how you'd need to raise it into a higher dimension, but it's not saying how would you separate them, it's just saying why can a linear classifier never perfectly separate these points. Okay, happy little bit of Dijkstra. So we start with A, which is labelled 0, given a permanent 0. we go 1 and 2. 1 is the best one, so we permanentize that one. Then from there, we go 1 plus 1 is 2. 1 plus 2 is 3. Best one now, I'm going to choose this version of 2. 2 plus 3 is 5. That's no good, so we wouldn't do that one. 2 plus 2 is 4. That's also no good, so nothing to update from there. We permanentize node C. 2 plus 3 is 5. There are no more outgoing edges. Oh, I forgot to do 1 plus 4, which is 5. That's not going to make any difference, luckily. Next, we permanentize 3. 3 plus 1 is 4. Makes no difference. Next one we're going to lock in is 5. And then that one is clearly 9. So we'll label them 0, 1, 2, 9, 2, 3, 5. Page rank is applied to this graph. Now, whenever we have page rank, I would be thinking to myself, have I counted for sync nodes? And yeah, so we need to imagine that D has sync nodes going to all the other nodes. Now, within this becomes a problem. In teaching the page rank algorithm, we often teach that D links to every node, including itself. However, in reality, although this isn't really used in reality anymore, we only link D to all the other nodes. Now, hopefully both would be okay. Hopefully we'll get some clarification on which one VCAR would like us to do. But I'm going to take the version where we only link from D to all the other nodes, which frankly seems to make more sense. I mean, why would you randomly jump from D back to itself? You know, that could be the case for anything. Now, really, we are just applying the algorithm. So we have 1 minus D, 0.2 divided by 7. So that is the chance of randomly getting to node F from a random jump, sorry, plus 0.8. We can get to F. Can we get that from A? No. B, we can. So B has a rank of 1 on 7. And B has 3 outgoing nodes. We can get to F from, let's do this the other way around. We can only get there from B or E. So E has, it's still got a rank, so they've all got ranks of 1 on 7 for that first iteration. E has 3 outputs, I think. 1, 2, no, it's got 2 outputs. And then we've got to consider D. So D is 1 on 7, and D I'm going to treat as having 6 outputs. So we would have had 0.2 over 7 plus 0.8, 1 on 21, plus 1 on 14, plus 1 on 42, which gives us 0.142, 1 on 7, 1 on 7. If you did it the other way, you would have got 0.1401. So both of those are debatably correct. This question, I didn't like the diagram, but you know, we have to be a little bit versatile with algorithmics. I think this arrow is pointing to this thing here. And this arrow is pointing not to the node, but to the grey bit. And when you think of it like that, you can see that it sort of makes sense that each box corresponds to a grey box. So we would call this thing here an input layer. So that's where we are starting. 5, I think is fairly obvious, is an edge weight. And this layer inside, given that we don't have any, we can't have inputs or outputs directly from it, this is the hidden layer. And the node up here is a bias node. Now, I've always seen bias as something you just add on as part of the weighting process, but we can just add a bias node as well. That just adds a weighting of 1, like a bias of 1, to whatever activation is happening for the node it's leading to. Now, again, you know, there might be different possibilities for this. If you thought that these boxes, this arrow here was pointing to the node, and you said that's a neural node, well, fair enough, because in fact they're all neural nodes. And we're told use one term from the list below for each box. Well, it doesn't mean that each box can only it doesn't mean that each term can only be used once. So you could have called 3 out of 4 of those things a neural node, and technically it will have been correct. But if that happens, try and ask yourself, is that really what you feel like the algorithmic examiner is going to be asking you? Then we had to calculate some stuff for these nodes. So we'll consider 1, 1. So 1, 1 has 1 times 1. That's this one here. It has x1, which was 3 times negative 2. It has x2, which is 1 times 3. So that is 1 minus 6 is minus 5, plus 3 is negative 2. Then we consider the activation for each one. And this is for every single node, not just the very last ones. Because that is less than 0, it has an activation of 0. So this outputs the value 0. Okay, what about for this node? We have 1 times negative 1 along the top here. We have x1, so that's 3 times 1, and we have 1 times 5, which is minus 1 plus 3 is 2 plus 5 is 7, and because that is greater than or equal to 0, the activation there is 7. Now we are considering this one because we're trying to find this activation value here. Let's get rid of those. We have 0 times 5, which is 0. We have 7 times 2. And we have the bias node, which has a weight of 0, which presumably would change during back propagation, which is 14. This gives us an activation value of 14. So the output value for this one is 14. Okay, try this one yourselves. And we're going to consider what is wrong with this question. So let's imagine we did this. We go, here is my graph, 1, 2, 3, representing the grid. And I'm going to try and represent the walk on the left. So I'll go, right, we colour that one, 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 that one. Well, I have no idea which order we're supposed to do this in. That could be this walk here, or it could be that I do it in this order. So we've got to make sure we store this in a way that the walk can be found. I mean, it's no good. You can't say you're storing something if you can't recall the thing that you were trying to store. The other problem with this, and this is a little bit more subtle, just because I've stored the graph in this kind of planar layout here doesn't mean the computer is storing that. So it doesn't know that the top left node corresponds to the top left square. You know, this could be stored scattered around memory or, you know, squished around. We don't know. It could be stored in like a straight line. 1, 2, 3. So this one links to this one, and this one, and this one links over there. Not there, but whatever. So the way I would address these two problems. Oh, and the other problem here. Let's just read this last sentence. Return all uncolored nodes, which to see which locations are unvisited. Now, that's not what it says. It says unvisited grid locations adjacent to a particular grid location. So we don't want to find all of the unvisited nodes. We just want to find the unvisited nodes next to a particular one. So let's take a better answer. We'll do this for the left-hand graph again. Label the node with a number to show the order in which it is traversed. So 1, 2, 3, 4, 5, 6, etc. 7, 8, 9. Also label the node to show where it is in the grid. So this one would be bottom left, or it'll be coordinates or whatever. So now we've stored the path in a way that can be recalled. To find grid locations adjacent, look at all the nodes adjacent and return the ones that have no path label. So let's say we didn't have these last two. and we wanted to find all adjacent locations to number 5, well, we look at the adjacent unvisited locations to number 5. We would look at 4, 2, 6, and the one on the right, and we'd say, oh, it's the one on the right. So I think the message there, read the question super carefully, and I think this comes up a lot. Try and think up a couple of different options. Don't just go straight for the first thing you think of. Okay, pause, have a think. This question, we have to make the important distinction. Are we modeling one particular instance of a problem using a graph or whatever, or are we modeling multiple instances? Are we doing a state graph? And that's what this is, and I think it's clear that's what this is after here. This could be used to store all of the arrangements of kangaroos and which ones could be reached from each other. So that's how I would be phrasing this. So, for example, we'd have one node which is 1, 4, 2, 5, 3, which would link to 4, 2, 1, 5, 3, and whatever else. Grace wants to see if the thing can be solved. Again, I thought this was quite gentle. I've said we can run BFS from a given starting point. We have to be a little bit more careful than just saying, oh, just run BFS or just brute force it. You could have done BFS, you could have done DFS, you could have done a minimum spanning tree to see if you end up hitting the node required. You could have done a SSSP algorithm as well. Pretty much anything would have got you the answer. But we need to make sure we answer the question, which is to say, how are we going to use our algorithm? So in my case, where I've done BFS, I've said we start from a particular starting point, marking the solutions as we go along. If we ever get to 1, 2, 3, 4, 5 before we've marked them all, then we can say the original starting point was solvable. But this one, again, we've got to be a little bit thoughtful. What are the examiners asking for? Okay, there are 3 marks. We're talking about time. We're, hardcore computer scientist, algorithmics type people. We want to mention time and complexity. So you've also got to be careful that we're only answering the question at the bottom. So it's the impact on reducing the time required to determine whether a new event clashes. So it doesn't matter how much preparation goes into it. I imagine a lot of people would look at this and say, well, number 1, sorting a list. Wow, you could use quick sort, but that's going to take potentially O of n squared. That's not actually part of our remit here. So if we have a sorted list, that can be found using binary search, which is logarithmic time. So this is, I reckon, what we should have said for this. Obviously, saying that number 2 is fastest because we know that dictionaries can be looked up very quickly in constant time. Don't say they can be looked up instantly. Okay, it's not instant. It's just in constant time. It doesn't get worse when the dictionary is larger. The searching ordered list takes log n time because we would pick a number, is the one we're after before or after, and then we'd halve our list each time in a binary search, divide and conquer manner. And searching through the unordered list for number 3 is garbage. It would be big O of n linear time. So getting those details down is the key for that question. Right, this is an absolute monster. I'm going to try and explain what we should have done. Backtracking algorithms are really hard to write. So I've had a crack here. I mean, I've looked at it a whole bunch and I haven't found a mistake with it, but who knows? Happy to accept your criticism and valuable feedback, etc. What I've tried to do is, rather than talk through, I've taken my algorithm and we're going to process it on a example. So when we first run find word, obviously let's just look at this very first call here. If C is in W and T is empty, well, no, that's clearly not the case. If C is not in S, well, we need to make sure, actually, I think this is a bit nitpicking, but we need to make sure or C is an empty string, or otherwise we'd have to put the empty string in S, which I don't think was done in the original. I could be wrong. Now we do for X in T, so for each tile, we're going to run find word with that tile. So that is this call, and this call. I haven't included every single call because I would have run out of space. So we start with this one here where we have A. So we're now on this call. If C is in W, no, it's not. If C is not in S, well, A is in S, so that was the word stem, so we're okay. So we're not going to return. Now we're going to consider AT. So when we do this call now, when we call AT, we find that AT is not in S, and so we return back up to this one. So we wouldn't actually make this call at all. So we'd return empty string up to this one. So it's impossible to start this with an A. So now we go down to this next one, and pretty much the same thing happens. I think I put AT in there to make the point for some reason. Yes, that's it. We had to say that T needs to be empty. So we can't just say that C is in our words. We have to have used all the tiles. That's one of the requirements. So this next bit here is pretty much the same. And the final call is where the final sort of first level down call is where the magic happens. And I've chosen the order so it doesn't run off the bottom of the page. We do CA, and then we choose another tile from there, which gives us CAT. And because C is in W and T is empty, we return cat. So this call here returns cat up to this one, which returns cat to this one, which returns cat. Okay, that would have been a monster to do. Again, this is one that you'll try and get like 50% correct and then go back and tweak it. Unless you happen to have been practicing backtracking algorithms. Okie dokie. What variables do we think we're after here? I'd say these ones. So just go through from the top. For j in 1 to length of test, so this is happening s times. So this is happening s times. When we assign the text to the sentence, so we can call that O of s, that is O of 1. And then, well, we're calling from line 3, we have to go down to this thing here. And we're searching, I mean, A is actually the sentence. So that is going to be W here. Well, it's going to be done in W times. So for I in 1 to the length of A, so that is the worst sentence there is. So that is going to be big O of W. And then for each of the words in W, if AI equals read, we're told in the little bit here that this happens in proportional to the length of the strings. So this is going to be the maximum letter of the word. So we could stick in some O1, O1. So the index here, this is going to be big O of W times L. And then this bit here is going to be O1. Writing, I mean, we're not told that anything else needs to happen there. We're not told that takes any longer. So now we've got line 1 is happening S times, and for each of those S times, we have line 3 which is happening. So that's W. So we have big O of S, W, L. And so we probably want some kind of explanation there. I mean, it's hard to really go beyond the there, but line 3 is called S times, and we'd say something like line 6 is called W times, and so on. I mean, I don't really feel like we're adding very much here. Well, we can say line W takes or runs in proportion big O of L. I think that might be one where you want to look at the examiner's report to get a better idea of exactly how to explain that, because I think annotating the code is probably as good as it gets there. One thing I've noticed in class is that people often don't like to use different variables. Now, the last few exams, at least the last 2 exams, have had different variables. So we're not just saying, oh, it's 3 things times together, so it's big O of n cubed. You've all seen For example, Dijkstra is is defined in terms of V and E, so we should be comfortable not just saying it's cubic, okay? Because it really depends on which thing is increasing. And I think the same mistake could be made here. We might not realize, or we might just ignore the fact that we are answering in terms of NL and NR. So we're told to annotate the pseudocode this time. And reading ahead, we can see that N is the length of P, so it sort of makes sense to use that. So we've got a constant time comparison here, another constant comparison here. That is going to be constant. However, this one where we are assigning a bunch of things to an array P left, this is going to be, I mean, it's n divided by 2, but we say that's big O of n. And this one here is also going to be linear because we have to go through every single item when we assign it. We can't just say, oh, you're having the left-hand half of that array. Okay. Then 9 and 10 are calling the closest pair. Algorithm again. Then we have min cross or check cross pairs. Actually, check cross pairs was the one that we wanted to compare, so I'm probably getting a bit preemptive because I know what's coming with this. For L in P left, so that is going to be NL. Then we have NR, and it's a simple double nested loop, really. We probably want to say that that is constant, and we're going to end up with big O of NL NR. Because it said to annotate the pseudocode, I would definitely put in the constant time bits as well. Okay, now we can see for part B, we can see this is calling itself a bunch of times. So we can see going to our master theorem, which I should really have put in. There we go. So we know that A is the number of recursive calls. So A equals 2. B is the amount we're dividing by, and it's half each time. That's happening on lines 7 to 8. So B equals 2. Now we have to consider what's going on the outside. Well, we know we've got the outer function is big O of n. So in fact, let's write this a bit better. We've got 2t n over 2 plus big O of n, and that seems to be happening twice. And then we've got big O of n squared, which has come from the NL/NR. At this point, we can sort of collapse the variables and say it's n because NL and NR are both determined, they're both half of n. So that actually makes a bit more sense. So we can see that in this case, C is going to be 2. I think you would have potentially lost marks here if you didn't go through that last little bit of process, as in talking about the work that's happening outside the function. If we just said, oh, it's quadratic, don't know, might be risky. The other thing people often miss, it says write a occurrence relation. We've also got to say 0, and that is when n is less than 2. Sorry, not 0, 1. So that is going to be our recurrence relation. So making sure we have that base case. Then we look at the master theorem. We have b to the power of c is greater than a. So we are dealing with this one, and it's big O of n squared. Hey, so a lot of people, I think, would get the gist of that, but it's getting all those details down in our recurrence relation that would, I think, catch some people out. Oh, this one! I would go straight away and write down that diagram, which you should be very, very familiar with. So we have P, NP, this bit is NP complete, and this bit is NP hard. So we have drawn a correct diagram in the box below. Well, the box isn't there. Just imagine it was. And what are the errors we've corrected? We've said P needs to be completely within NP, and we've said NP complete needs to just be between NP hard and NP, is in the intersection there. So we need to say that P is just this bit here, so there's no P outside of NP, and there's no NP complete outside of NP or NP hard. So really, these should be together. So we want to now explain those errors in terms of the problem definitions, which I have done here. So the first sentence for the first paragraph, all problems in P are also in NP. And now we've said why with reference to those definitions. NP means, well, if you can verify a solution in polytime, that means if you can solve it in polytime, well, it's also verifiable in polytime. So everything everything in P must be in NP. Definition of NP complete is it's the hardest problems in NP, and NP hard is the ones which are at least as hard as the problems in NP. Whoops. As. Therefore, it must be the intersection of those two things. This one, guys, just learn your definitions. Simple as. Alright, it's fiddly, but go with it. Okay, let's go back to saying, is this a good answer or is this a bad answer? Okay, now, the one in red, I mean, that's the clue, isn't it? The one in red would get nothing, I hope, because you haven't really talked about the Chinese room argument system response. You've just said the Chinese room argument again. So what we should have said was, describe the only real reply that I can think of, and certainly the first one, probably the only one that everyone learns. If the man memorizes all the rules, he would then be able to apply those rules. Isn't that what happens when you learn a language? You start by translating things back into your own language, but yeah, I don't think it's the best answer, but it's the standard one. Right, what do we think about some responses to this one? Now, this is kind of all right, but firstly, it does not look like 3 marks. And I feel like a question like this is really asking us to say, are there other counter-arguments? Which this response here, yes, there are other counter-arguments. So many others, all kinds of other ones. Make sure you do name some. Don't just say, no, it's not the only other one. There are, oh my goodness, just imagine how many. And to get our 4 marks, we will have want to go into a bit of information about what those responses are. I'm not going to get into the details of the CRA now. That's the kind of detail I think we would be aiming for this question. 18. Now this one, I saw this and thought, oh, you know exactly the mistake people are going to make, because this really feels like you're going to put a node here and a node here and a node here, because they look like nodes, don't they? And then we'll join them up with edges, won't we? And then maybe some edges there and there, and that looks just like the situation. How will I use that to define traffic lights? Well, I don't know, just brute force it. Which, by the way, if you ever write just use brute force, ask yourself if you can go into a bit more detail, because brute force will not help you here. What we needed to do was consider this as a conflict problem. And as soon as you think about conflicts, hopefully you are thinking graph coloring. So for example, imagine I'm going from Police Road to the Prince's Highway South. So we'll call that Prince's Highway South, Prince's Highway North, and Springvale Road South, Springvale Road North. So if I'm turning around this way, well, that's okay. I can also have traffic going from Police Road to Centre Road. That's no problem. And I can have traffic going from, so just taking this one as my frame of reference. So traffic can also be going that way. What we couldn't have though is Springvale Road North traffic going to Prince's Highway South, for example. So we couldn't have traffic coming from here down to here. Let's assume this isn't one of those nice gentle, filter lane bits. So we would have an edge there. So what we actually have to do is draw a graph with all of the different possible traffic routes and then stick an edge between them to indicate that they can't happen at the same time. Okay, it's really counterintuitive. You're not going to end up with a nice graph, but that is the aim of what we had to do. And I have described it thus. There are 6 roads. Each one can go to 5 different destinations. We're considering both directions. So Police Road to Prince's Highway is not the same as Prince's Highway to Police Road. Hopefully you guys are familiar with driving enough, given your age most likely. So why that's the case. And then we've just described this, add an edge between a pair of nodes where traffic cannot traverse them simultaneously. Then we want to talk about the graph coloring problem. Here, I mean, with graph coloring, we're probably thinking simulated annealing or backtracking. It's not very many nodes, so we can probably do this with backtracking. And I've started by saying exactly how we would do that. Start with 2 colors, 3 colors. I could probably go, for this answer, maybe go into a bit more information on what that means for brute force or backtracking. But hey, you may get away with it. Making sure we've then said what the color will represent. Each color will then have all the nodes that have the same color are nodes that can happen at the same time. They're traffic paths that can happen at the same time. So we could have this one and this one would have the same color, but it would have to have a different color to, I don't know, this one. So I've got my lefts and rights mixed up, but you can probably see what's going on. Okay. Final question. I think people will have been surprised as to how this went. It's quite a nice proof by contradiction here. I'll just give you a minute to try it out, then we'll talk through and we'll look at the amount of detail here. Because I think the temptation is to say, assume the algorithm makes an invalid plan. Well, the instructions show that it doesn't, so your initial assumption must be wrong. Like, yeah, great. Let's get a bit more detail down. So this is the level of detail we would have been after. And again, reading the question, they've given us all this information here. Let's try and use that. Let's use that to our advantage, to show that we've paid attention. So when we go to line 4, so J is like different subjects. So is that right? No, sorry, J is students sitting subject J. Because we go IJ and then we swap them here, which goes JI, that means every time we move along the row, we are changing the subject. So for 2 students sitting the same exam, the subject would have to not change, and that would have to be because there's only one subject, but we're told n is greater than 1. So that's a contradiction. What if they were sitting behind each other? Now, this is a bit sneaky. Imagine there were, imagine the row was 6 large. Okay, this is our row of things. And then our subjects are going to be, let's say we had 2 different subjects, like X, Y, X, Y, X, Y. Now you can see we are going to get people seated behind each other. If we used 5 different subjects, let's call them just 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1. You can see they're never going to line up. They're certainly going to line up like row after row. So, and it's a bit mean that this is a little bit of mathematical theory, but hey, your method students, they've shown you it's 13. That 13 must have something interesting about it. Other than the fact it's unlucky, number of factors is the fact it's a prime number. And if you play around with the possibilities, you can see that that's the only way that the students sitting the same exam could be seated one in front of the other. Our final question. Here we go. I've mentioned throughout this video that we want to plan and think about our answers before we get into them. And we do obviously want to talk about, I mean, it says define the relevant variables. Well, let's just jump into that and say, yeah, number of subjects, average students per subject. There's a bit of flexibility here. We might have had an array showing the number of students in each subject. And we can define, I mean, I've mentioned here, if you only had one subject and you had the number of students was more than half of the number of seats, then it couldn't possibly be done. Because you can imagine a sort of checkerboard situation. If we had only one subject, they'd have to all be separate, like this. This occurred to me as I was writing the model answer here, not model answer, but I thought, well, if S is greater than 1 and ST is, so the number of students is less than 390 divided by 2. Well, in fact, we don't even need to say if S is greater than 1. If the number of students is less than half the number of seats, well then we can just put everyone in whichever order, leaving an empty seat between each one. So considering those edge cases show that we've thought about it, it also leads us to think about empty seats, which I think is one of the slight variations on this thing as a simple graph coloring problem. Well, I've got our idea of mapping nodes as seats, subjects are colours, and I've mentioned black is going to be an empty seat. Edges connect adjacent seats. Now, the first time I wrote this, I thought, well, let's go simulated annealing, random number of plan. Yeah, this is all the same stuff. I've mentioned black seats can be next to each other because they're empty. But then I thought, well, let's compare that to the alternative. The alternative would be brute force, and we've got to work out whether a particular set of subjects can be scheduled for the same examination session. This isn't something that's being done over and over. You haven't got your phone and you're not navigating across the centre of Melbourne at rush hour and you need an answer quickly. This could be done over a long period of time. You could set this off to work out over a week because, yeah, it's not an urgent situation. So I decided in the end, in my final answer, I would use all this stuff. So I'd probably get rid of that. I would include this and I'd probably just scratch that out. This is not exactly an essay writing course, so as long as all the ideas are there, it doesn't matter that we've been a bit casual with our English. So I would use backtracking, and then I've tried to describe exactly how I would use backtracking. And as always, I've described, well, how will I know the answer? I will know that if there are no colours left to assign before the graph is finished, then it's not possible to make a valid seating plan. I hope this has been useful to you. Leave your comments, subscribe for the next one, and good luck in your exam or your results whenever you watch this video.